Hello, everyone. Welcome to Talk Talk Speak podcast. Today, we're doing something a little different. Instead of our usual format, we're taking a deep dive into the fascinating 30-year history of NVIDIA, a company that has evolved, from a graphics chip pioneer to the very core of the artificial intelligence revolution. Think of this as your shortcut to understanding how a company born in a Denny's came to power the AI giants.
Yeah, and we'll be unpacking the key moments and insights from, well, a detailed account of NVIDIA's journey. We're tracing its evolution and those really pivotal decisions that shaped its destiny.
Right. Our goal here is to extract the most crucial knowledge nuggets, the surprising facts, the turning points, maybe those aha moments that explain NVIDIA's current dominance in AI. And we'll try to do it without overwhelming you with too much technical jargon. We really want to understand how a gaming graphics company became the engine of the AI revolution. Okay, let's get right into it. The story begins, believe it or not, April 5th, 1993. Breakfast meeting, Denny's, East San Jose.
It's quite the origin story. And what's interesting right away is the founders' backgrounds. You've got Jensen Huang, who came from LSI Logic and AMD.
Okay.
And then Chris Malachowski and Curtis Prime, both from Sun Microsystems. And funny enough, they'd actually worked together before on a pretty challenging project called the GX graphics engine when Huang was at LSI.
Ah, so they had some history, even some tough history.
Exactly. And that experience, though difficult, seems like it planted the seed for NVIDIA.
And it was in that Denny's, a place Huang apparently knew from his teen years.
Ah, really?
Yeah, that's the story. That's where they hammered out this core idea. Graphics processing wasn't just for, better-looking games. It held the key to solving really complex computing problems that regular CPUs, they just couldn't handle efficiently.
That's a pretty big vision for 93.
It was huge, so strong that Huang actually left a stable job to chase it. That takes serious conviction.
A massive leap. And they started small, with their own money. Around $40,000 total, apparently.
40,000? I heard maybe even less, like $600 initially.
Well, the exact number varies, but it was definitely bootstrapping at first. Then, pretty quickly, they got that crucial $20 million in venture capital. Sequoia Capital, Sutter Hill Ventures.
Big names.
Very big names. That early backing must have said something about the potential they saw even back then.
And the name, NVIDIA, it's got a cool story too, right?
Yeah, it's a mix. NVIDIA, which is Latin for envy.
Envy, okay.
And NV, the chip code name, stood for new vision or maybe next version.
So aiming to make the competition envious.
Pretty much. And Huang, even though he was the youngest, he became CEO. That says a lot about his leadership early on.
But it wasn't smooth sailing from there, was it? Their first product, NV1 in 95.
Oh, far from smooth. The NV1 was incredibly ambitious, like a Swiss Army knife graphics card. It tried to do 2D, 3D, audio, video. Even had a Sega Saturn gamepad port built in.
Wow, talk about feature creep, trying to do everything.
And that ambition really backfired. It was expensive, way too complex.
And here's the key technical bit, right? It used a non-standard way to draw 3D shapes, quadratic surfaces.
Exactly. Quadratic surface rendering. Meanwhile, the whole industry, especially Microsoft with DirectX, was standardizing on triangles.
So games just wouldn't work right on it.
A lot of them wouldn't, yeah. Compatibility was a huge issue.
And the fallout was bad.
Almost catastrophic. Diamond Multimedia, a major partner, returned. Get this, 249,000 out of 250,000 chips.
Ouch. That's basically the entire order, a near-death experience for the company.
Absolutely, a true make-or-break moment.
But then Sega comes along, a potential lifeline, right? They got a contract for the NV2 chip for Sega's next console.
Yes, but here's the crazy part. They actually doubled down on the non-standard approach. They planned to use quadrangles again for the NV2.
Wait, even after the NV1 disaster, going against the DirectX standard again?
It sounds unbelievable, doesn't it? It put them in an incredibly tough spot. Continue with Sega, invest maybe 2 more years in an architecture diverging from the PC market.
Or cancel the contract and risk immediate bankruptcy.
Exactly. A true bet-the-company decision.
And Huang chose to cancel. A huge risk. But the negotiation, how did he pull that off?
It's legendary. He somehow convinced Sega to pay the full $5 million contract amount.
Even though NVIDIA delivered nothing.
Even though they delivered nothing. That $5 million, it literally saved the company. No exaggeration.
Just incredible. That kind of negotiation skill. Wow.
It absolutely did save them. And those early struggles, those near-death moments, they were incredibly formative. They learned the hard way about pragmatism, about flexibility.
Right. They had to adapt.
After NV1, They finally shifted away from their own proprietary tech and embraced the industry-standard graphics pipeline. The one SGI, their competitor, was pioneering.
So learning to follow the market instead of fighting it?
Precisely. That willingness to adapt became really crucial later on.
And you have to think the founding team's skills were key here too, right? Priam on architecture, Malachowski on engineering.
And Huang on management, and clearly business deals.
Yeah. Those complementary skills must have been vital to navigate those crises.
No doubt. And that new pragmatism started to pay off. 1997, they launched the RVA-128, or NV3. This time, the focus was laser sharp.
Yeah.
Booming 3D graphics market for PCs.
Okay, so learning from mistakes, what did it do well?
It supported both 2D and 3D acceleration, and crucially, polygon texture mapping. That's wrapping images onto 3D shapes.
Making things look more real.
Exactly. And its specs were genuinely competitive, better than 3DFX's popular Voodoo 1 in some ways, like core speed.
And it sold well.
It was a real commercial success. Good price, integrated features, solid direct 3D support. It hit the sweet spot.
They followed up with a faster version too, the RVA-128ZX.
They did. They were finally building momentum, finally on the right track.
Good. So moving into 1998.
1998 brought the RVA TNT, or NV4. TNT stood for Twin Texel.
Twin Texel, what does that mean?
It meant the architecture could process 2 texture pixels in a single clock cycle. Nice performance bump. It also had better overall performance, 32-bit true color rendering for better visuals, AGP support, and competitive pricing again.
But there was something else important happening around then, wasn't there? Something about software.
Yes. And this is easy to overlook, but so important looking back. Their early focus on drivers. They branded them detonator drivers and really committed to ensuring game compatibility and performance.
So the hardware was good, but they made sure the software actually delivered.
Exactly. That built a strong reputation with gamers and developers. And it helped them land those huge OEM deals with Dell and Gateway.
Getting their chips into mainstream PCs.
Right. And that early software focus, it really foreshadows how critical software, specifically CUDA, will become later. They got it early on. Hardware needs great software.
Okay, so late 90s, NVIDIA is a serious player. 1999 rolls around. We get the Ryve TNT2.
Which was basically a faster, more refined TNT. Smaller manufacturing process, higher speeds. Solid, but evolutionary.
But then later in 99 came something revolutionary. The GeForce 256.
Ah, yes. The GeForce 256. And NVIDIA made a very bold marketing move here.
They called it the world's first GPU, right? Graphics processing unit.
They did. Now, technically, they weren't the very first to use the term GPU, but they absolutely popularized it. It was a strategic move to differentiate it from older 3D accelerators, to signal something new.
And it wasn't just marketing spin. There was real tech behind it.
Oh, absolutely. The core breakthrough was hardware transform and lighting, TNL.
Okay, TNL, break that down for us. What did it actually do?
So before GeForce 256, the main CPU had to do a lot of the geometry calculations for 3D graphics. Figuring out where objects were in 3D space, that's the transform part, and calculating how light hit those objects to create shadows and highlights, that's the lighting.
And that took up a lot of CPU power.
A ton. Especially in complex scenes, it could really bog down the system. What the GeForce 256 did was offload all that heavy lifting, the TNL calculations, directly onto the graphics chip itself.
Freeing up the CPU.
Exactly. Freeing up the CPU for other tasks like game logic and AI. And the performance boost for 3D was massive. Estimates were around 4 times the triangle processing power compared to high-end CPUs at the time. A huge leap.
And other innovations, too. Architecture, memory.
Yep. 4 rendering pipelines, which was advanced for the time. And it was the first consumer card to use DDR SDRAM.
DDR memory. That meant much faster data access, right?
Significantly faster memory bandwidth, yes. Crucial for feeding those pipelines. And it fully supported DirectX 7.
So the market reaction must have been pretty strong.
Immediate and profound. It cemented NVIDIA's technical leadership. It really kicked off the dominance of the GeForce brand. It also contributed to the decline of their main rival at the time, 3DFX. ATI became the main competitor after that.
And beyond just games, that TNL integration, it changed things fundamentally.
It really did. It changed the whole architecture of the PC, the division of labor between CPU and GPU. It definitely hinted at this future where the GPU could do more than just draw pictures.
Which leads perfectly into the Quadra line, using that same GeForce 256 tech for professionals.
Precisely. NVIDIA saw that the power of the GeForce 256 wasn't just for gamers. It was hugely valuable for professional workstations. CAD, digital content creation, that sort of thing.
So same basic chip, different target market.
Pretty much. They took the GeForce 256 chip, internally called NV10GL, paired it with certified, highly optimized drivers for professional apps, added some specific features, maybe more memory, and boom, the Quadro line was born.
A smart way to leverage their core tech into a higher margin market.
Very smart. A great example of segmenting the market effectively.
And this kicked off a period of really rapid performance gains, right? The Huang's Law era.
Yeah, for several years there, the performance increases were relentless, almost annual. You had GeForce 2 with more processing units, then GeForce 3, which was revolutionary with its programmable shaders.
Programmable shaders that allowed for much fancier visual effects.
Way more complex and realistic effects, yes.
Huh.
Then GeForce 4 refined things. GeForce FX aimed for the next shader level, maybe stumbled a bit.
I remember that one being controversial.
It had its issues. Then GeForce 6 brought Shader Model 3.0 and SLI, linking multiple GPUs together.
Right, SLI. I remember building SLI rigs.
And then GeForce 7 in 2005. Just constant iteration and pushing the envelope on graphics.
And we shouldn't forget the original Xbox partnership with Microsoft in 2001.
True. Now, even if it wasn't hugely profitable initially, putting their chip inside millions of Xboxes, that was huge for brand recognition and technical cred.
Okay, so NVIDIA is king of the graphics hill. But then they start looking beyond graphics. This is where it gets really interesting for AI, right?
This is the pivot. They started realizing the fundamental architecture of their GPUs, this massively parallel design.
All those cores designed to do similar calculations simultaneously for graphics.
Exactly. That SIMD architecture, single instruction, multiple data, it had potential way beyond just rendering pixels. It was perfectly suited for tackling other kinds of computationally intensive problems that CPUs, designed for serial tasks, struggled with.
It's like having an army of specialists versus a few generalists.
That's a good analogy.
Yeah.
But actually using GPUs for non-graphics tasks, what became known as GPGPU.
General purpose computing on GPUs.
Right. Back in the early 2000s, it was really, really hard.
You basically had to trick the graphics software, like OpenGL or DirectX.
Pretty much. Using shader languages, trying to map your scientific problem onto graphics concepts, it was clumsy, inefficient.
Steep learning curve.
Very steep. And the graphics APIs had limitations. Memory access wasn't flexible. Support for things like integer math was poor. It just wasn't designed for it.
So NVIDIA saw this bottleneck, this potential, and decided to build a better way.
That was the vision. To create an easier, more efficient platform to unlock the GPU's power for general parallel computing. And that vision became CUDA.
CUT Compute Unified Device Architecture.
And the development was led by Ian Buck. NVIDIA hired him in 2004.
He'd already done work in this area at Stanford.
Yeah, with a language called Brook. He was a pioneer. The goal for CUDA was simple. Create CC++ extensions, let developers program the GPU for parallel tasks without needing to be graphics API wizards. Make it accessible.
And the CUDA platform launched in 2006. It was more than just a language extension, wasn't it?
Oh, much more. It was a complete solution. Our programming model with concepts like kernels, threads, blocks, grids to organize parallel work. A defined memory hierarchy registers. Shared memory. Global memory giving programmers control for optimization.
Which is crucial for performance.
Absolutely. Plus runtime libraries, driver APIs, the NVCC compiler, debuggers, profilers, the whole toolkit.
And it fixed those GPGPU limitations. Better memory access, integer support.
Yes. Things like scattered reads from memory, user-managed shared memory, easier CPU, GPU data transfers, full integer and bitwise operation support. It was a huge step up.
So a game changer for scientists and researchers.
Transformative. And to support this, NVIDIA also launched dedicated hardware, the Tesla line.
Right. Starting with the G80 architecture, same as the GeForce 8800.
But differentiated. Early Tesla cards often didn't even have display outputs. They were purely for computation. More memory, better double precision performance, optimized for scientific workloads.
And did the scientific community embrace it?
Rapidly. We saw huge speed-ups in molecular dynamics, physics simulations, medical imaging, bioinformatics, financial modeling, you name it. CUDA accelerated breakthroughs.
And NVIDIA made a really smart move making the CUDA software free. Right?
Brilliant strategy. Free software, but it only ran on NVIDIA hardware.
Locking people into their ecosystem.
Exactly. And they poured resources into building that ecosystem. Great documentation, tutorials, support forums, optimized libraries like Kubernetes and CuFFT.
Those libraries handle common math tasks super efficiently.
Right. Saves developers tons of time. They even worked with universities to create CUDA courses.
Training the next generation on their platform.
It was masterful. CUDA wasn't just tech, it was strategy. It shifted NVIDIA from a graphics company to a parallel computing platform company. The power of software and ecosystem realizing the hardware's value, ease of use, performance, compatibility across GeForce, Quadro, Tesla. It all clicked.
And that platform thinking perfectly positioned them for the AI explosion. Which brings us to 2012 AlexNet.
The spark. Before AlexNet, machine learning for things like computer vision relied heavily on manual feature engineering. Think SIFT, HOG algorithms.
Trying to tell the computer what features to look for in an image.
Exactly. And it struggled with real-world complexity. Deep learning, especially convolutional neural networks, CNNs, had theoretical promise. But progress was slow, limited by lack of large data sets and, critically, the sheer compute power needed for training.
Until ImageNet came along, the big competition.
Right. ILS-VRC, that was the proving ground. And in 2012, Alex Krzyzewski, Jeffrey Hinton, and Ilya Sutskever from the University of Toronto.
Hinton and Sutskever, huge names in AI now.
Absolutely. They entered AlexNet at deep CNN. Innovative architecture, yes, but the key was how they trained it.
On NVIDIA GPUs using CUDA.
Bingo. They used 2 off-the-shelf GeForce GTX 580s. Consumer cards.
Seriously, not some specialized hardware.
Nope. 2 gaming cards, 3 GB of memory each. And using CUDA's parallelism, they trained this massive network in just days. On CPUs at the time, it would have taken weeks, maybe months.
And the results were stunning.
Revolutionary. AlexNet won ImageNet with a 15.3% top 5 error rate. The next best competitor was over 25%.
That's not just winning, that's demolishing the competition. A huge leap.
It was the watershed moment, the Sputnik moment for AI and for NVIDIA. It proved deep learning works spectacularly well, and that GPU acceleration was the way to do it.
Jensen Huang talks about this being the moment they went all in on AI. Right?
He does. He saw the future. It changed NVIDIA's entire focus. They started optimizing everything for AI, even thinking about self-driving cars way back then.
Another major strategic shift.
And they doubled down on the software side, too. In 2014, they released CUDA.
Okay, CUDA. What did that add?
It's a CUD library, specifically optimized for the core operations in deep neural networks. Convolutions, pooling, activation functions, the building blocks. It made these operations run incredibly fast on NVIDIA GPUs.
So it made life much easier for people building AI frameworks like TensorFlow or PyTorch.
Massively easier. Framework developers could just plug into CUDA for optimized performance instead of coding it all themselves. It accelerated the whole field. Google used it heavily for early TensorFlow.
And they actively engaged with the research community too, didn't they? That DGX-1 donation to OpenAI.
Right, in 2016, the very first DGX-1 AI supercomputer, packed with 8 Tesla P100 GPUs. OpenAI used it to train early versions of their large language models, the precursors to GPT. A huge symbolic and practical gesture.
It really shows the synergy, doesn't it? AlexNet succeeding on consumer hardware highlighted CUDA's power.
Which drove more AI research, which created demand for more powerful NVIDIA GPUs.
A classic positive feedback loop.
Absolutely. Which leads us into the era of NVIDIA consciously architecting intelligence, building AI acceleration right into the silicon.
Starting with Volta in 2017 and the birth of Tensor Cores.
Tensor Cores. These are specialized hardware units inside the GPU.
Designed for one specific thing?
Pretty much. Designed to accelerate matrix, multiply, accumulate operations, the mathematical core of deep learning training and inference.
And they use some clever tricks with numerical precision.
Yes, hardware, software, co-designed at its finest. The first-gen Tensor Cores did the main multiplication using lower precision FP16, but accumulated the results in higher precision FP32. This hybrid approach gave a huge boost in throughput raw calculation speed without sacrificing too much accuracy.
So faster AI training and inference.
Much faster. The Volt V100 had 640 of these cores, plus faster NVLink for GPU-to-GPU communication and faster HBM2 memory.
Then came Ampere in 2020, more improvements.
Further enhancements. Third-gen Tensor Cores supporting more precisions like TF32, BF16, even FP64 for scientific computing, plus a feature called structural sparsity, basically skipping useless calculations with 0 values in the network.
More efficiency.
And multi-instance GPU, or MIG, that allowed data centers to carve up one big GPU into several smaller, isolated virtual GPUs. Better utilization.
Smart for cloud providers.
Very. Plus faster memory, HBM2E, and faster NVLink again. Constant iteration.
And then Hopper in 2022, specifically targeting transformers and LLMs.
Exactly. The rise of models like GPT needed specialized hardware. Hopper introduced the transformer engine.
What does the transformer engine do?
It's clever. It combines 4th-gen Tensor Cores with software that dynamically chooses the best, fastest numerical precision FP8 or FP16 for different parts of the transformer model.
So optimizing on the fly for speed and efficiency.
Right, resulting in massive speed-ups, especially for inference-running models like ChatGPT. Up to 30x faster inference, they claimed, compared to Ampere. Plus faster HBM3 memory, 4th-gen NVLink, confidential computing features. The H100 became the AI workhorse.
And now, 2024, Blackwell. This sounds like another huge step, dual die design.
It's a monster. 2 massive chips fused together on one package, pushing past manufacturing limits. 208 billion transistors.
Just staggering numbers.
And a 2nd-gen transformer engine supporting even lower precisions, FP4 and FP6.
Even faster, even more efficient.
That's the goal. More compute, less memory bandwidth needed, potentially lower power for certain tasks. 5th-gen Tensor Cores optimized for this. 5th-gen NVLink for scaling up to huge systems. 576 GPUs working together. Enhanced security, faster data decompression hardware.
The GB200 NVL72 rack system sounds insane. 30x LLM inference boost over Hopper.
That's the claim, along with better power efficiency and cost. And they're talking annual updates now. The pace is just relentless.
So you really see this clear progression. Dedicated AI hardware, smarter precision, faster interconnects, scaling.
All driven by the needs of AI. It's hardware, software, co-design on a massive scale.
But again, it's not just the hardware. That ecosystem fortress.
Crucial. CED is now this vast platform. Core language, drivers, compiler, yes. But also those optimized libraries we mentioned. Keblaze, Hefty, CUDA, Tensor 8 for inference optimization.
These libraries let people get performance without being CED experts.
Exactly. NVIDIA does the heavy lifting, optimizing them for their hardware and for frameworks like TensorFlow and PyTorch. It's a huge value add.
Plus the developer tools, documentation, community support.
They make it easy to get started and get help. Lowering of the barrier to entry fostered this huge community. CUDA is used everywhere now.
And the cross-generational compatibility protects developers' investments.
Right. Code written years ago often still runs, maybe even faster, on new hardware. That builds loyalty.
And creates massive switching costs.
Huge. Rewriting code for a different platform, learning new tools, risking performance drops, it's a major deterrent, even if a competitor has similar raw hardware specs.
They don't have the CUDA ecosystem.
Not to the same extent, it's NVIDIA's moat.
And strategic partnerships amplify this. The cloud providers.
Deep, long-standing ties with AWS, Azure, Google Cloud. They're huge customers and distribution channels.
Yeah.
NVIDIA's AI enterprise software, NI microservices, they're all available easily on these clouds. DGX Cloud, too.
Though it's a bit tricky now with cloud providers developing their own AI chips, too.
It is. A delicate balance.
Yeah.
Partnership and potential competition down the road.
And the university collaborations.
Key for research advancement and talent pipelines, like the AI Center at University of Florida with the latest DGX systems, or the Quantum Computing Center in Boston. They're training the next generation on NVIDIA tech.
And the Inception program for startups?
Over 15,000 AI and HPC startups. NVIDIA provides tech support, marketing help, funding connections, training. It integrates future innovators into their ecosystem early. We see successful Inception startups everywhere: agriculture, healthcare, energy.
So it's hardware innovation plus masterful ecosystem building.
It's the combination that's their strength.
And boy, are they reaping the rewards now. The AI gold rush, the numbers are just mind-boggling.
Exponential growth is an understatement. Revenue going from, what, $16–17 billion in FY21 to potentially over $130 billion in FY25.
Driven almost entirely by the data center business.
Over 90% of revenue in recent quarters. Their data center revenue alone dwarfs competitors like AMD, Intel, IBM combined in that space.
Profitability through the roof, market cap hitting $3 trillion.
And market share in AI accelerators estimated between 70% and some say up to 98%.
Almost a monopoly in high-end AI training chips.
Pretty close. Around 3.76 million data center GPUs shipped in 2023, mostly NVIDIA. A100, H100.
Yeah.
They're the standard for LLMs.
And the demand from cloud giants is insatiable, leading to shortages and high prices.
Exactly. H100 is going for $25K to $40K, Blackwell maybe $35K to $50K, DGX systems costing hundreds of thousands. They have immense pricing power right now.
And they don't even make the chips themselves. TSMC and Samsung do.
Which just highlights the value isn't just the silicon, it's the architecture, the interconnect, and crucially, the CUDA software ecosystem. Customers buy the whole platform.
A platform competitors are finding incredibly hard to replicate quickly.
Very hard. Meanwhile, their traditional gaming business, while still significant, is growing much slower.
Yeah, saw an 11% decline last quarter. The focus is clearly data center AI now.
It really is. NVIDIA's current success is the payoff for decades of focused vision, sustained investment, and some very smart, sometimes risky bets on graphics, parallel computing, and ultimately AI.
So you see, this deep dive into NVIDIA's 30-year history reveals a truly remarkable journey. Constant adaptation, some unbelievable strategic risks,
Mhm.
and this relentless pursuit of innovation, from those Denny's napkins, basically, to powering the entire AI revolution.
It's an incredible story, a testament to clear vision, building that ecosystem, and yeah, maybe making competitors a bit envious.
Hopefully this has given you, our listeners, a clearer picture, not just what NVIDIA does, but how they got here, why they're so central to AI.
It's so much more than just faster chips, isn't it? It's this whole platform built over decades.
Absolutely. So what stands out to you most in this evolution? Are you maybe curious about the challenges ahead for them? Competition? Ethical questions around such dominance?
These are definitely important questions as this AI story keeps unfolding so quickly.
And consider this final thought. NVIDIA's early bet on parallel processing for graphics, which seemed kind of niche maybe,
Right, just for games initially.
it unexpectedly positioned them perfectly for the AI explosion years later. What seemingly niche tech today might unlock the next big leap. Something to think about. Thank you for joining us. See you next time.